This method can help answer key questions in physics and chemistry, such as which bonds are broken first or how atoms and electrons rearrange during a chemical reaction.
This technique's main advantage is that the extreme ultraviolet radiation from a free-electron laser, or FEL, can act as a site-specific probe because it only ionizes specific atoms within a molecule.
Learning to achieve spatial and temporal overlap between the FEL and optical laser beams benefits from visual demonstration because very specific diagnostics are used and the effects can be subtle.
Demonstrating this procedure will be Dimitrios Rompotis, physicist at the Flash Free-Electron laser at DESY.
First, verify that the ion detector, the electron detector, and the high voltage power for the ion spectrometer electrodes are turned off. Close the FEL and optical laser shutters using the instrument software. Configure the filters and attenuators installed in the beamline so that the FEL pulse energy and the optical laser power are reduced to less than 1% transmission. Then, insert the Cerium YAG beam viewing screen into the interaction region. Open the FEL shutter and examine the screen via a CCD camera. If the beam spot is not detectable on the screen, slightly increase the beam intensity. Once the beam spot has been located, mark the FEL beam position as a region of interest in the camera data acquisition software. Then, open the optical laser shutter and close the FEL shutter. Adjust the steering mirrors to align.